Hello, friends. Wanted to just take a look at the homework, see if we can get started with the homework right quick. I'm going to try to work through problem 3.1. So make a little note here to myself. It's going to be problem 3.1, number 7. Okay, I'm going to go ahead and share my screen. Um, so this is the assignment. This one is not going to be a discussion, so you're not going to be seeing everybody's document get uploaded. You can reference back to the first round of homework and you can see a lot of folks doing some good work there. Now, what I wanted to go through with y'all is a little bit of how to find the resources again, because I feel like that's important. So here's our syllabus. And inside the syllabus, we've got quite a few fun things that we can use. So let's do this one first. And actually, yeah, that'll work. So I'll just wait, open this up in a new tab. Okay, so now we're down to 3.1 and number 7. And it says, describe an algorithm that takes an input of n ints and finds the last even or return 0 if no evens. Okay, so this one I'm going to do just a little bit differently. I'm gonna take a stab at this first and just see how this goes. So here's my hover camera, and we're gonna, on my nice monitor, this looks fine. But I understand that on yours it may not. So I'm going to say let's say address equals 0. And then I would say for if oh, and I should say and then I'll say if num at that address is greater than or equal to max even, then I'm going to come in and I'm going to say and I'm going to change this up here. I'm going to say, make this one say max address. So I'll come down here and I'll say max address equals address. Okay, so that's not a great description, but that's hopefully enough to get you started. So I'm going to go ahead and share my screen again. And so that's the question. Let's come back here to the resources. And there we go. Wait. Goals, clean code. So I think it is in here. Oh, that's the syllabus. Couple of copies of PDF. Even answers. Nope, this is an odd. So we'll want odd. $100 pages to sift through, and that's okay. We'll try going down about this far. That's not quite far enough. This will be a bit of an eye chart. We're getting close. At least I feel like we're getting close. Oh, yep, there's 3.1. So I'm going to see if I can make this bigger. Okay, now we need to find number 7 and see what they have. They usually have pretty strict definitions. So this is 3.1. So procedure, last even location of these inputs. We'll start out with k equals 0 for I equals 1 to n, where n is our number of integers. If a is even, then k equals I. Oh, it's not, it's just looking for the last one. So this one, let me go ahead and stop my share right quick. I had made a mistake. It's not necessarily the max even. This one was the last even. So for all the addresses in the list, if the num at that address this is kind of a syntax that we use in Java and a lot of other languages. Basically what this means is, hey, we're going to probably have this in some sort of a list. Maybe it's an array, and that array is going to have addresses. So we'll just go to the individual address and then take that number, divide it by 2. And what's the remainder? If the remainder is 0, then and so what this will do, it'll assign our last even to that address and then just keep going. And so that's, I'll go ahead and share my screen again. That's what we're seeing here in this description here. Basically at the bottom it says return address, and we can see that if there are no evens, then it's still going to have an address of 0 as long as we just start at an address which is greater than 1. But again, that's not necessarily guaranteed. And if you're working in a language like Java, where the first address is 0, then I would probably encourage you to return a -1. Okay, so that is how we work through. I'll go ahead and share my screen again. That is how we work through this first question. Hopefully that's fairly straightforward and easy to understand. All 3 problems, hopefully it's just describing an algorithm. I would like it if you could follow the jargon and the terminology that they use in the book. And Appendix A actually has some of the description of how they come up with this notation. But if you want to do it like I did it, just using paper and English or even a programming language, that's completely fine as well. So the second one is an in distinct integers and finds the location of the largest even integer. And that's the problem that I was starting to work through initially, where I was keeping track of the largest one. So that's, hopefully you can see that these 2 are similar, and you'll have a definition of this in the even answers. And then it says the last problem is a palindrome. It's the same forward and backwards. Describe an algorithm for determining whether the string of n characters is a palindrome. So of course, let's just talk about that right quick. So let's talk about a palindrome. So we'll use Bob as an example. So let's give these the numbers. 1, 2, 3. Okay. And then 4-letter palindrome. Let me see if I can find one right quick. Noon. We'll use this as an example. So this is 1, 2, 3, 4. So I guess the first thing I would say is if length modulo 2 is 0, then we're going to say even. And so if, let's call this our lists. And we'll say if list of 0 dot equals list of n. And so we can put this in a for loop for position equals 0, position less than length position plus plus, right? And so we can say instead of this, we could just say actually, let's make this length over 2, something like that. The idea is we're just going to check the first half of the numbers. And so what we'll do is instead of list, we'll say list of position dot equals, maybe it needs to be a square bracket. I don't know. I mean, ink pen syntax, right? And then we'll say list of, and we'll say this, it should be n minus 1. I'll put that in parentheses. And then I'll take away from that position. Okay, so I will admit my brain's not working on this. My brain automatically went to this. So let's say position equals 0. So if we're looking at list of position equals 0, that's going to be n. So this is just kind of a fun example. And so I'll just mark this in a funny colored pencil. We'll call that first part n dot equals, and so I'll just shorthand this. Hi, Dr. Parker.
This is yours.
All right, friends, I apologize. I lost my train of thought temporarily there, so need to get back. So let's take a look at these numbers right quick. If our list is length n, so our list of, if it's length n minus 1 would be 3. So 4 minus 1 would be 3. Minus position is 0. So this is position 3. So we would say n equals n. So that would be a check. And then we would say we would index position to 1 because of our for loop. And so list of position 1, this would be O. And then we're going to check against, so list n would be 4. I should say instead of n, this should probably be length. Okay, so length is 4. 4 minus 1 is going to be 3. Minus 1 for position is going to be 2. So we check, and that is an O up there. So O is equal to O. Okay, and this is of course number 9. So finally, for the other ones, you'll probably have like an else, not even, and then you're going to do from position, you're going to go from in to length over to, you're going to round that down. That's this is the symbol for rounding things down. Anyway, you'll round it down and -1. Actually, I don't think you need to do -1. I think you can just round it down. Okay, so let's look at what that would be. This has a length of 1, 2, 3. So 1, 2, 3 divided by 2 is going to be 1.5. And so we're going to go to 1. And again, I'm sorry, my brain wasn't thinking right when I wrote this. You'll check, actually, you'll stop before you get to 1. So you'll just check, does B equal B? Yeah, we're good to go. We'll get a 5-letter palindrome. So let's just, as another example, do kayak. So 0, 1, 2, 3, 4. So we've got a length would equal 5. 5 divided by 2 equals 2.5. Rounding this down is going to be equal to 2. So you're going to do position equals 0 up to position less than 2. And so we'll verify that K is equal to K, A is equal to A, and that's where we stop. Okay, friends, so that was a bit of a rush, and I admit that. What I would like to say is, as far as references in the book is going to talk about how to describe algorithms and things. It's also going to give you a few hints on the notation that you can use. Also, as far as assumptions that you have to make, just assume normal numbers and assume that we can follow the definitions in the book. So not a big stretch this time. And then when we're talking about doing the work, this is kind of it. It doesn't have to be real complicated. And then finally, why do you trust your answer? Well, we trust it. The first one, we were actually able to go in and, we could kind of walk through this in our mind, or maybe even write a code off of that. Actually, I should say the first one was there. The second one was basically an extension of the first, and they just kind of went together. And then the third one with the palindromes, we were actually able to use our algorithm and test a couple of palindromes. So friends, that's what I have for today. Hopefully you have a lot of fun, and I look forward to catching up to you later. Thank you all for your time, and let me know if there's anything I can do to help. Take care.